teaching model number 5, we take a look at how to determine the number of significant figures when we're given a recorded piece of data, and in particular, how do we work with having zeros in our numbers? The following rule sounds quite complicated, but if you understand the meaning of significant figures, then knowing the rule is not quite so important. The rule states that one should start counting digits where the number first takes on a non-zero value, and then stop with the digit whose value is uncertain. So let us see how this works. Consider the example 1. Leading zeros are not significant. For the number 0.0031, the first non-zero value is the 3. The next and the last digit is 1. This number has only 2 significant figures. If we reflect, however, why would we write those zeros at the beginning of the number? Those zeros are not telling us anything about how certain we are about the measurement. Rather, they indicate how big or how small the numerical value is. A better way, of course, would be to record this number using scientific notation, that is, 3.1 times 10 to the negative 3. The leading zeros are not significant because they simply indicate how big or how small the overall number is. For example 2, trap zeros are significant. Once again, it's helpful to ask why would we write a 0 in between a 3 and a 1, unless the 0 is indicating information about the number in the measurement. We are certain about the 3, the 0, and we're guessing about the 1. This has 3 significant figures. For example 3, tailing zeros are significant if they come after a decimal place. In this example, the leading zeros indicate the size of the number and are not significant. The digits 3 and 1 are significant. Again, we ask, why would we add this extra 0 after the 1? This 0 does not say how big or how small the number is. Rather, the 0 tells us about the relative certainty of our measurement. We are guessing at its precise value. Therefore, this number has 3 significant figures. For example 4, tailing zeros without a decimal point, however, can be ambiguous. For the given number 350,000, we really have no idea how many significant figures are present. The best guess would be 2 significant figures, as the zeros are written to indicate the size of the number. A better way, of course, would be to put this into scientific notation as seen in example 5, which shows a number that clearly has 4 significant figures. Another less common approach is to place an intentional decimal at the end of the zeros. The second number in example 5 shows 6 significant figures. In the last part of this activity, we will look on how to attend to significant figures when we manipulate numbers in terms of either multiplication and division or addition and subtraction. In teaching model 6, I will give an example of an addition and a subtraction. Look carefully at the example and see if you can divine the strategy used in this approach. When we add or subtract numbers, the number with the least digits past the decimal place will dictate the number of significant figures in the answer. In the addition example, it is the middle number, the 10,000.1, that dictates that the final answer must have only 1 digit past the decimal place. The final answer has 6 significant figures. In the subtraction example, it is the top number, 445.8, that dictates the final answer must have only 1 digit past the decimal place. The final answer has 4 significant figures. When we multiply or divide numbers, the number with the least significant figures will dictate the number of significant figures in the answer. In the multiplication example, it is this last number, 26, that dictates that the final answer must have only 2 sig figs, or significant figures. In the division example, it is the denominator, the 0.0920, that dictates that the final answer must have only 3 significant figures.